Well, good morning. So, what is it, October 15? Is that right? 12. 12. Okay, October 12th. This is the Cosmology Discussion Group meeting for October 12th, 2025. And this morning, Robert French is going to talk to us about his atomic model. So, that sounds interesting. I think this came up at the last time Robert talked, he was asked about his atomic model. So Robert has kindly agreed to give us a discussion about his model. You need to send me a request, Robert.
Okay, let's see. Remind me where I find request.
It's a green tab at the
Your
bottom.
green tab where it says share.
Yep.
Okay. Send request. Okay.
There we go.
Okay, so I hit share again.
Now you want to click on, you should have a screen that opens up the different windows and you click on the window and share screen.
Okay. Let's see. Okay, here we go. Share. Okay, can you see it?
Yes, very good.
Okay, I'll try. Let's see. Slideshow. Let's see. Slideshow from beginning. Okay, how's that?
It's going, working now. Fine. Thank you.
Okay, fine. Models of atomic physics, and I give my email and my website, which posts my ebook, A Model of the Physical World. This actually involves material I haven't presented before, and I've worked on and on for it for quite a period of time. And I've always been interested in defending physical realism. And if nothing else, this is a physical realist model of the atom, including electron orbitals, but also of nuclei. It's
Okay, Bob, why don't you explain what you mean by physical realism?
that
Just
something exists physically. At a minimum, the atoms exist physically. It's not just a calculating device, even though we're not immediately aware of atoms. So they have their own independent existence apart from us. And I try to push this as far as I can, and a lot of it's pretty speculative. But I try to have at least be consistent with experimental results that I'm aware of. And I'd love to get some feedback on some of this to get it better, but it's about as good as I can get it at the moment.
okay, how would you characterize the current thinking of mainstream physics? Is that physical realism? I don't really consider it to be physical realism,
I
I
tend
guess.
to agree. I mean, there's a mixture, which there is in any subject. But for an awful lot of people, their training is in mathematics and they consider what they're doing like mathematical calculating devices for making predictions or known results. There are some physical realists out there, so it's a mixture, is the real truth. But for an awful lot, it's just a calculating device, and that's historically been known as positivism. But I'm trying to defend physical realism in any event.
Okay, that was a
Okay.
good summary, by the way.
Yeah, okay. Yeah. Yeah. I want to go through this, I think, reasonably slowly. I mean, and I'd rather get to the end before very many questions. But in any event, let me begin. Let's see if I can get slides to go. Okay. Okay, I want to start with the periodic table of elements. I think it was Mendeleev who originally came up with this. And there's an important observation. I'm not the first person to notice this, but I don't notice it always gets emphasized all that much. And that is the length of each row is 2 to the n squared, where n is the principal quantum number. So you start with hydrogen and helium, there's your 2. Then you have 2 plus 6 equals 8, which is 2 times 2 squared. Then you get in the middle, there's a group of 10. So you get 6 plus 2, 8 plus 10 is 18, which is 2 times 3 squared. And then you get those real long groups of 14, the lanthanide and actinide series, where you have 14 in each of those. And so there it's 2 times 4 squared, or 32. And this kind of raises an issue whether this order in the periodic table is due to something like a packing issue. I tend to think that it is, because as you go out, I think I pointed this out before with my thin shells, the area goes as r squared. So here you get an n squared, which tells me that maybe this has something to do with packing. Okay, let's see my next slide.
Would you
Okay,
explain what you mean by packing?
okay, the way in which things are packed together. I did do some packing issues with my model of the nuclei at the very end, but it tells me the way in which electrons are packed around the nucleus. In my model of, I hate point particles, so I think of electrons as being spatially spread out, in fact, spatially spread out over entire orbitals. So the way in which those orbitals are packed together, that's where I think you get this n squared ratio going on. Okay, and here's my model. I came up with this one. I don't know as anyone else has, and it's probably not the only possible model out there that's possible. But in any event, here uh, I have the principal quantum numbers go out at an r squared rate, uh, but not all of the orbitals are occupied, but they become occupied in the subshells. Like first orbital, of course, you have the s quantum number, or with chemistry, and there you have like 2 electrons with opposite spins. Then for the p, uh, which has, let's see if I get this right here. Okay, the P has 6 electrons, and if you count out the orbitals, you come up with 3, and then because you have 2 for the spin, it's 2 times 3. And then for the D, you have 10 electrons, so we come up with 5 there. 5 times 2 gives you your 10. And the F1, which is not shown here, you would have 14 electrons. And in the middle here with my with the dots, that represents the equipartition of mass in a possible orbital. And the arrows, and notice my arrows, they get smaller as we go out. And this would follow from the conservation of angular momentum. The velocity is going to decrease as you get out. So as the radius increases, to keep angular momentum a constant, the rectilinear velocity has to be 1 over r. Okay, here I talk about empirical evidence that the radii of atoms actually increases at r squared, an n squared rate. This actually, first off, both the Bohr model and the modern quantum theory, they both claim this. How serious they are about it, I think, is a good question. And again, it probably depends on the individual. But I know with the old quantum theory, and here you have to look at Niels Bohr on the constitution of atoms and molecules back in 1913. He actually points out that more spectral lines can be detected in higher and higher vacuums. I know that I mentioned this once to Ed Dowdy, and when I talked with him, he told me about a very recent talk that had been given at NASA Goddard by this Rashid Soniev. And he pointed out that you get enormous values for the principal quantum number with light from astronomical light from the cosmos, and it's high here as an n equals 30, and this has actually been observed. So in other words, the greater the vacuum, and of course you'll have very good vacuums in outer space. As far as I can see, the resulting atoms, if you take this seriously, would be enormous. But there's nothing for them to bump into in a very good vacuum. So I take that as some empirical evidence for taking this literally, that the principal quantum number corresponds to the radius of the atom. Let's see my next slide. A derivation of the Balmer formula. This has been known for a long time. 1 over lambda equals the Rydberg constant times 1 over, you have the two quantum numbers, the one for the upper orbital and the one for the lower orbital. Both are squared. So N1, the principal quantum number for the upper orbital, is interpreted as the radius of the upper orbital. And N2, the principal quantum number of the lower orbital, is interpreted as the radius of the lower orbital. And the radii would occur in quadratic increments. And the second N2 is always greater than N1. And then since the circumference is 2 pi r, the circumference of the upper orbital it will be 2 pi r, which uh, 2 pi r for the first orbital, and C2 will be 2 pi r for the second orbital. And then since we assume the
Oh, that's
conservation
not
of,
R squared,
that's right.
Robert?
Yeah, that would be R
2 pi
squared.
R is the correct formula, right?
Oh, yeah, excuse me. So it's 2 pi n, and then n goes as R squared. Okay, I hope I have that right. Okay. But excuse me, let me go back one. Okay, so assuming the conservation of angular momentum, since r is proportional to n squared. Yeah, thanks for pointing that out, Jim. That should have been 2r pi r. Okay, assuming the conservation of angular momentum, since r is proportional to n squared, 1 over r is proportional to 1 over n squared. Using Bohr's angular momentum postulate, this can be initialized in terms of the respective angular speeds of the orbitals, omega 1 and omega 2, occurring in integral increments of nh over 2 pi. And the difference in the time of rotations, okay, that would be the period of the respective orbitals to catch up with each other, that is for their radial angles to realign, would be 1 over n1 squared minus 1 over n2 squared. So I try to correlate this with the emission of light, and it's a little bit sketchy here, but if that's the going to be the period of the light, 1 over the period will be the wavelength. And so maybe that has to do with the way in which light is emitted for individual photons. That's about as good as I was able to get that, but let's see. Then I also have one for the energy, Balmer formula energies. Since kinetic energy is proportional to the squared rectilinear velocity, and both r is proportional to n squared, and the angular momentum is directly proportional to n, it follows that the rectilinear velocities of the orbitals being jumped between will be proportional to 1 over n, and since kinetic energy is 1/2 mv squared, it'd be proportional to 1 over n squared. That's as good as I could get for the energies of the orbitals. It does raise issues about how you account for negative energies, which are postulated by the old quantum theory and by the new quantum theory in terms of the ideas that like electrons, bound electrons, are in a potential and it takes additional energy to free the electrons. I also take note that an issue for my theory here is Rutherford scattering. That's the way in which they found out how small the nucleus is. with scattering experiments with alpha particles and beta particles, alpha particles being helium nuclei, beta being free electrons, because it seems like nothing is blocking them until they hit the nucleus, in which case they have to be going through these electron orbitals. And how exactly that's going to occur with my model, I think, is a good question. So I raise it as a possible issue to be dealt with.
Would the additional energy required to free the electrons be related to the photoelectric effect?
Well, certainly the photoelectro effect, that's where the electron is released from the orbitals. And so if you have a photon with high enough energy, then yeah, the additional energy sends the electron off, which is measured with the photoelectron. Yeah, so it is related, yes.
Thank you.
Okay, let's see, my next one. I have several on spin. I've actually shown these ones before. My account of spin is if you have a constant rectilinear velocity on a spherical surface, then above the equator, you'll have like, say, counterclockwise rotation, and below it, you'll have clockwise rotation. And again, my model has these of an ideal liquid. So by just postulating a constant rectilinear velocity within the orbitals, you can account for these for spin up and spin down, the two spin states. Let's see, the next one, I think I've shown these before also, where this spin vector is twice the length of the one for angular velocity. And I tie this in, as Feynman points out, with rotations in a liquid, the vorticity vector is twice as long as the one for angular velocity. So I show this for a unit circle, and in particular, in the case of where there's in a magnetic field, the component of the electron's magnetic moment is proportional to the cosine of the angle. And then this one is just a diagram from Hertzberg showing how you have a precession occurring in the presence of a magnetic field. And again, the spin vector is twice the length of the one for rectilinear velocity. Then let's see, I have one here for covalent bonds. Covalent bonds are sort of interesting. The concept actually goes back to Gilbert Lewis, but also Linus Pauling talks about the structure some. And it's kind of a paradoxical language they talk about sometimes as an electron being shared by two different atoms. And how you get that to happen with anything like a point particle is kind of beyond me, if you want to take it literally. But here I show a diagram both for deuterium, hydrogen-2, where the electron orbital is going to be around both of the nucleons, a proton and a neutron. And then for a hydrogen-2 model, a stable hydrogen, and there, with the orbitals, I have them go around both, but they're separated with the first orbitals. And there I try to show how within one, let's say the outermost, you can have the two opposing spins in terms of my the vorticity being in different directions. And as Pauling points out, for the bond here, you can have two electrons, but they have to have opposite spins. Okay, my next diagrams, this is highly speculative. I worked this out actually, I think my first couple of years in college, and how serious to take this, I don't know. But I have a few diagrams on the structure of nuclei. Here's my first one. And here I take nucleons as being spheres, solid spheres. and is in a nucleus as being literally adjacent to each other. So again, you can have sort of like a packing issue here. And I've tried this with marbles, putting them together with clay. Some of this you can illustrate just like working with pennies and putting them next to each other. But helium comes out real nicely as a tetrahedron. Uh, so you have three grouped together in one layer, and then you put right in the center in the second layer. So that's a real that's a structure which has a lot of stability to it, the tetrahedron. Now, in order to get this to work at all, the next move sounds kind of counterintuitive, and again, I'm not real sure how serious to take this. But if you put four of the helium nuclei as tetrahedrons together, that's going to equal 16. And that is the atomic weight for oxygen. And I've done this with a model. You put the four together, and it's interesting. You get a gap right in the middle, but it's a real symmetrical shape that you come up with. So that's my model for for oxygen. But you have points on each of the ends. You have four of those points. And if maybe with collisions, you got rid of all of those points, then you have a nice layer around everything. And the nice layer around everything, that is 12, which is the atomic weight for carbon. Uh, so in any event, it's interesting if you continue putting them around the carbon and get another whole layer around everything, okay, you end up with 56, which is the atomic weight for iron. And iron is also very common in the universe. So all of these have this space in the middle, which I would say doesn't have a nucleon. And so I give some other ones. These are ones with the oxygen base. And I played around with this some. There probably are other variants, but it's interesting that you come up with the most common uh, elements in the universe as having the most stable structures with this model. And I make some points here at the end. Features of the proposed nuclear structure. There is a model which Fred Hoyle came up with in the early 1950s, the tri-alpha process. And there it would be three helium nuclei combining to make carbon. 3 times 4 would equal 12 for the carbon. But of course, with my model here, what would come out first would be oxygen. So it differs from the tri-alpha process proposed by Hoyle. How good the evidence is that it's 3 and not 4, I'm not sure. But then you have this cycle going on, the oxygen, nitrogen, carbon cycle. So you have a cycle going between those three stable nuclei, and it produces a helium nucleus. So it sort of ties in fairly interestingly with that process. And then I say that there are complete shells for hydrogen, helium, carbon, and iron. And this fits in pretty well with how common are in the known universe. Hydrogen, 74%, helium, 24%, carbon, 0.4%, and iron, 0.11%. Let's see. Can you hear me?
Yes.
Oh, okay. I'm partly frozen up, unfortunately, here. Okay. And so I just got an error message. But in any event, that's actually the end of the presentation. And that's about as far as I was able to come up with things. And it is speculative, but
Okay. Well, I think a lot of other people have come up with this packing approach as well.
you may know more than I do on it, Harry, and sometimes people come up with things independently of each other. That's about as far as I was able to push it. Whether anyone has the details the same as me, I don't know.
Yeah, it seems to me some people have used magnets to do the packing idea, and because the magnets sort of form these structures, if you put them together and they kind of fit together in these packing structures. Um, I've seen people do it that way. Um, I'd like to go back to the covalent bond thing.
Yeah, okay, let me go back to that one.
I'm kind of interested. I was kind of curious where you say you said you didn't really feel that comfortable with the idea of a point electron.
Well, but where is the point electron if it's being shared by two different atoms?
Right. Um, so maybe there's no such thing as a point electron.
I don't believe, and let me run across the cons and whether they, I mean, the mathematicians, I think, like point particles. And you can get issues about repulsion. If the electron has parts, why doesn't it explode with repulsions? But I tend to explain repulsion not within a particle, but in terms of my shells outside of a particle.
Okay. But so you don't really have a model of the electron per se. And
I tend to think of it as spread out over an orbital, which would at best be a model of a
right.
bound electron. I definitely don't have a good model of the free electron, and you got to be careful there because free electrons, they both have particle characteristics like charge and mass, and they seem to be located when they're absorbed by something else at a sharp location, but they also have wave properties, like with electron diffraction experiments, and how you put that all that together in a coherent way. Something a little funny is going on, and I'm not sure what.
Can we go back to the shells?
Sure. Let's see. Shells.
Back to the beginning, right after the
This
periodic
one.
table. Yeah.
This.
So what you're thinking is that the electron. Whoops! What happened to it? Is it still there? I don't see it now.
Well, we lost
Robert.
Oh no. Oh, okay. Well, that wasn't good.
He'll be back.
All right. Well, I guess we need to fill in some time here. I was, I'm kind of intrigued by Robert's statement that he doesn't think electrons are localized as point particles. And he's saying that they're spread out on the shells. Do you have any comments on that?
So that would seem
Of
to.
the book I'm actually going through at the moment, which is The Universal Force by Lucas. He has a similar conception, although I don't know if his ideas of spreading out would be quite as severe as Robert's, but he's talking about these torus shells with spiral,
Right.
you know,
Well,
orbits.
here we got Robert back again. At least he's trying to show up here. I know that Lucas has. I'm kind of of the opinion that to talk about an electron is in a way um, kind of misleading because it then that leads you to this idea that it's a particle. As soon as you say particle, then that implies that it's this tiny little thing, and that implies mathematically it's a tiny little point. And then now you sort of it, to me, I don't really see the electron as being that. I see it as more like what Robert was talking about.
Yeah.
I'm certainly open to that conception.
Well, I'm kind of a cat person where I think more of electricity as being a wave than as being particles. So to me, the idea that an electron is spread out implies to me that it's more like a wave. It's
I think you have to work with, yeah. I think you have to work with both concepts and try to get aspects of both together. And if nothing else, you want consistency with a model. But so maybe both of the classical concepts of a wave and a particle, you have to take aspects of both. And certainly at a minimum with the particle, I would say is to get it to be spread out.
Well, the fact that you can't hit an electron when you're shooting at it very easily in the Rutherford experiments kind of means that it's, I guess the mainstream interpretation is that its probability of its being in a location is negligible, and so therefore you can't really hit it.
Yeah, and depends on what sense of probability you have going
Right.
on there. And probability, like there's the ignorance approach, there's the propensity approach, and I think at the moment they seem to go more with the propensity approach than the ignorance approach. Ignorance, it has an exact location, you just don't know where it is with that exact location.
Right. Right.
Propensity doesn't even have that until you make make a measurement. Or people talk about clouds and things, and uh, I don't know. There's a genuine issue there, and I don't know as I have a better solution than anyone else to it.
Well, right. That's where we're into the conundrum. Could you explain what I think you used two terms there. One was ignorance, and the other was propensity.
Yeah.
You might, well, we got a few, we have like 8 minutes here, but
Yeah, okay. Ignorance is something has an exact property, you just don't know what it is. Like, say, if you're throwing dice, two die, then it's 1 in 12 for a particular combination. And if you go into all the details, it's actually maybe even determined to come up a certain way, but you just don't know which way it's going to come up. Uh, that's ignorance. So there is an exact property, you just don't know what it is. Propensity is, I keep running across this concept in physics. Uh, some people bring in Aristotle here, where they talk about having a potential to become something else. Now, usually when you say something has a potential to become something else, like you say that a child has the potential to become an adult or something, it already is something else, and then it just changes what it is. Or say, but a caterpillar has the potential to become a butterfly or something like that. But here, some of them don't even seem to be saying that. They're just these propensities, which are not even concrete something else's. It's just that in the right circumstances, sometimes it does be, turn into something happens, and so you just talk about the propensity before this, and the whole subject, to my mind, gets pretty murky there. Although sometimes they can throw in probabilities here and say that there's a probability for becoming something. It's just you can be detailed with your probabilities, but it's still not clear what exists until like say a measurement is made, or something is detected, or maybe just absorbed, if you don't want to bring in like subjective language about knowledge, which I tend to like that, to say that like wave packets, that they become reduced, I say, upon absorption. And there's some paradoxes you have to deal with, like with superpositions, even for saying that. But yeah, so those are at least two different senses of probability. There's also the sense of like over the long run, occurrences over the long run. Like people for working for insurance companies, actuarians, they work with that concept. So yeah, probability is more than one sense.
But is propensity in those terms always a temporal thing? I mean, you gave examples about something becoming something else. Could one say, well, look, there's a propensity for this at the same time to be a number of things?
Okay, you could have the propensity, I suppose. You want to say outside time or at a given moment.
Yeah.
Yeah, I suppose it could be outside time or at a given moment. It has the propensity, and then as time elapses, something happens. So the propensity itself, I don't know as that has to be temporal. But it gets pretty murky if you don't say that it's something else that has the potential to
yeah,
become something.
I see now, I see now why you want realism. You want,
Yeah,
you
you're
want,
starting to get into philosophy here.
Yeah,
it is
that's my
philosophy.
background, and that's my background's philosophy. Yeah.
But that's why you find out that philosophers are um, in quantum mechanics. You don't see philosophers, but a lot of them are interested in quantum mechanics because of these issues that Bob's talking about. And so then you have this question of Bob has sort of gone on to the idea of physical realism, which I can kind of see why he's in that realm of thinking about it.
Well, I think it has a huge explanatory power. Why does something happen? Or you make an observation. Why does it happen? If you say there's something out there causing it to happen that actually exists, I think that's a good explanation for why something happens. If you just say you're dealing with calculating devices, and it says nothing about why they work.
Well, it's about cause and effect. It's
Right.
always about cause and effect. There's always an action and a reaction.
Hmm.
And as far as the atom is concerned, they and molecules also behave like a wave. So we
Yeah, I
can't,
know. It gets it.
we have to say that atoms are solid mass and molecules are mass because they make up elements. And
I know they've
we
even
have to
done.
say that electrons are mass as well because they behave like waves as well.
Mhm.
I mean, the fact is that there's a medium and there's movement through the medium, which we see as light, photons of all kinds of flavors, X-rays, the whole spectrum, the whole EM spectrum is all photons at differing energies, and that's the medium. I'm almost sure of it. And there may be even particles that we have not even detected, or quasi particles of matter that we haven't even detected yet, that we don't even know about, that helps consist of allowing EM to flow. And atoms allow EM to flow, molecules allow EM to flow, electrons allow these discharges from the sun. That's where EM flows. There's three sources of EM: galactic centers, suns, and plasma. Plasma clouds, or I shouldn't say clouds,
We
plasma.
only got a minute here, so
Uh,
you,
my point is that until we understand what the electron is exactly and fully understand what it is, we can just keep guessing and guessing and guessing.
I
We
would.
have to.
All
Well,
right.
that was my point. Is just that we don't know, and until we know, we we just guess, and
Well,
we
you can have an intelligent guess is one point, right?
yes, but I mean, I take the electron microscope as an example. These electrons are hitting an object in the center target area, and they're bouncing this way or that way or this way and hitting a detector, and that allows the mathematics to be able to give you an image of what these electrons are bouncing off of. They have to be a point particle at that point.
Why
No,
is that?
they have to be because they're hitting something and bouncing off of it.
Well,
Yeah, but
a
That's
point, a
that's
point
that's a
can't hit anything. In
sorry.
the geometry that I took in elementary school, a point has no dimension. It can't hit anything.
Well, a particle I meant, a point particle.
Right.
You mean a
So,
localized point particle with perhaps
Yeah.
a limited radius,
so
not
we're
spread
back
out, but
to
not
the,
points. Yes, that's correct, which has no dimension.
There
we're back
must
to
be a
the,
finite size, I believe. By the way, you mentioned the three things: the plasma, suns, and a third one that create EM radiation. I have a little device called a lamp on my table, and I can turn it on, and it gives out light. And it's not a
Yeah.
sun.
That's an
It's
arc
not a plasma
that's an arc discharge.
in my lamp.
Yep.
I don't think so. It uses
That's a that's
LEDs.
yeah.
My lamp has a light bulb that uses LEDs. I actually
right.
smashed one and took it apart and saw it. My God, there's LEDs in here.
Mhm.
It's still an arc discharge. It's producing light like an arc discharge would.
Yeah. Do you know on that, Harry, how LEDs work?
yeah, it's sort of, yeah, not that easy to explain. So I'm not an expert on that. Um,
Might be a question of terminology. One wouldn't think it's an arc discharge. It's a different phenomenon. But
well, I think what he's saying is it involves electricity. It involves electricity, and so
That part's true.
what's really happening is that we're talking about electricity in two different ways, and that's and some that's the paradox of the wave particle duality. We use in electricity, we have a model that these electrons are flowing down wires, okay,
Yeah.
as material particles, as these point particles,
Yeah.
and it's a
One,
material flow
one
of
point to
electrons.
make, one point to make, and I usually make this with photons, but you can make it, I think, with electrons also. And that is that, like, when it's emitted, it's from a very small region. When it's detected or absorbed, that's also a very small region. But what happens in between, you're not actually observing. And that's where I think that things get very spread out. But there's something about like the absorption process, it just grabs it. And of course, I'm not a big fan of special relativity, so this can occur faster than the speed of light. It's just during the time of like absorption. So it may be grabbing from a very big region and from multiple sources also. I definitely say that for photons, and I'm tempted to say it for electrons. Like even in chemistry, they talk about superpositions of electrons, like even for like a single electron, in which case, yeah, maybe it gets split up and then recombined. But whenever it's detected, it always has these nice discrete properties. But it doesn't mean that those nice discrete properties are occurring when it's not being detected. I tend to think that they're not, but it has to. But emission and absorption, they both are quantized, so they have to occur in discrete amounts. And it's kind of speculative what happens in between.
Well, you just described wave particle duality.
Yeah, and I'm a realist throughout it. And Bohr, I hate. I like the early Bohr. I hate the later Bohr because Bohr talks about complementary properties and things and revels in contradictions. And I don't revel in contradictions. If nothing else, the physical world should be a consistent world.
Yes, you would hope so, but kind of my view about it is that the contradictions arise because they're trying to explain things they don't really understand.
And
And
you
so
have to
we're
rework
giving them,
concepts also sometimes. And you don't have to be tied to traditional concepts.
right. And in quantum mechanics, I think it's problematic in special relativity as well. That you're trying to explain something that's not thoroughly well understood. And so these magical ideas appear.
Yeah, I
things
don't
that,
know if any of this is all that well understood. And there are things which, like half-lives and things, which really do look to be probabilistic. And again, is that just because we don't know everything that's going on? And you would think some of these ought to be like not reversible, like an atomic bomb going off. You're doing like the half-lives for unstable uranium nuclei and things like that, U-235. And but once it's gone off, it seems like there was a really point in time when something occurred, and something occurred at a specific point, and it has nothing to do with someone making an observation here. I think an atomic bomb going off. Then, yeah, it sounds like maybe they should push a little bit more of the ignorance approach. There's something actually more going on, like with within the U-235 nucleus than we know about. Maybe they're not all absolutely identical. Maybe there are processes occurring inside that we just don't know about. But they try to take probabilities
Possible to
here as
reverse these
basic.
things?
What's
Or
that?
is it just very, very difficult? You know, the Humpty Dumpty syndrome, it's so difficult. All the king's horses and all the king's men couldn't put Humpty Dumpty together again. But is it theoretically conceivable that one could reverse a nuclear explosion?
Uh,
That's quite a deep
that
question.
is. I mean, some other ones maybe are reversible, and often like you have issues occurring, like with the concept of entropy, whether the disorder is basic or whether it's just a measure of our ignorance. In some processes, it's just very unlikely to reverse them, but maybe like but creating, say, like an ice cube, like from water and stuff, where the water molecules combine together just randomly in the right way, you could produce an iceberg. That's just incredibly unlikely to occur. So that's the ignorance approach versus there's something fundamental there.
well, can we go back to your covalent bond diagram?
Let's
The
see.
issue
I
that I
think I
have,
lost my diagrams. Let's see if I can hit share again. Send request.
so I'm back to the issue of this covalent bond. I see that as kind of uh, an important point, which is how is it possible the way they're explaining it and talking about it? I don't really see how it's possible.
Yeah, they do talk about the electron being shared. And how, with the classical concept of an electron, that makes sense. I think it's a real good question.
Well, it implies that an electron has a point, a position, um, and that somehow the position is in the is at two atoms at the same time.
Yeah.
Is that the um, idea somehow or another that it's not really at one atom and it's not really in the other, it's in both at the same time somehow?
Something like that. And you can make sense out of that. The original theory, evidently, Gilbert Lewis, who actually was the first person to came up with the term photon. He came up with a lot, but yeah, I also read like Linus Pauling on it. But yeah, it's like there's some sense in which it's being shared, but exactly what that sense is under the traditional chemistry has never been clear to me.
I think I've even seen them use the term cloud, which seems to be against all their conceptions, but I think they have used that rather
Yeah,
than.
I think what they would say is that the cloud encompasses both atoms, that
Yeah.
this electron somehow or another has a probability distribution that encompasses both atoms. But then you're sort of faced with this question of now you've got probability cloud. Okay, what does that mean? That's not realism according to what Bob is thinking.
Not
That's
if not if it's the propensity concept of probability. The
what
ignorance one maybe you could try to hold on to, but then you can't account for some of the wave properties and things if you use the ignorance.
Well, when you look at an atom, through an electron microscope, through the most powerful ones that we have, we see shells represented as these atoms of each
Well, I think
particle.
you're talking about, they look like spheres that are kind of packed together.
Yeah, exactly. That's our understanding of an atom at the moment. We look at these outer shells, and how is it that an electron can be orbiting so fast within that atom or around that atom that it makes that shell look solid?
That's kind of the Bohr conception, like
It would have
planets.
to be traveling faster than the speed of light in order
That
for that to happen.
that part doesn't bother me, but I think you're sort of working with the Bohr conception that it's like a little solar system, and that's not my concept.
I was just going to get at at how about the electron encompassing the atom, expanding out to cover the entirety of the atom. And this would help explain for these strange shapes that we see for these shells from some elements.
Yeah. Now you might note this. If you're talking about a photograph of this, it's typically time-lapse photography.
The video, there's videos of atoms, gold bridges breaking, and you can see once the bridge is broken, you can see atoms sliding along and reattaching to the main group of atoms on each side.
But even there, you need multiple photons just to make the image.
Right.
Well, yeah, it's electron microscopy.
Right.
But
So
that's making the image. It's not photons, right?
Oh, okay,
you're
electrons.
you're using electrons to make images of atoms. And obviously what's happening is that there's a reflection. The electrons are reflecting off of the atom atomic boundary, if you will.
The shell, yeah.
So we see it as a kind of a spherical thing. At least the pictures that I've seen, and most of the ones that I've seen are the static images where they show the atoms stacked in lattices.
Yeah, lattice.
And they say, well, this is what an atom looks like. Well, yeah, I'm not sure exactly that is a meaningful statement. Because it depends on how you measure, what your measuring technique is. It's not like looking at it with a ray of light, although they are using electrons as if they were light.
Yeah, and of course, the process of looking, that may disturb what you're looking at.
I think that's a misnomer that they're using electrons as light. I think they're just using the geometry of the electron bouncing off of the surface to see what that surface is is made or shaped like or made
Yeah,
of.
but the theory is similar to the idea of light being reflected off of an object that you photograph.
Right, yeah.
And so the idea is that you're looking at a photograph of atoms, although it's not photo, it's not, so it's more of an electrograph.
Electrograph,
If
yeah.
you like, yeah. Of course, there you're using free electrons again.
Right.
And your picture is of them as having sharp trajectories. And how do you also account for wave properties of free electrons?
Well, that's where the free electrons do have wave properties, and that's kind of what makes it work.
Well, I mean, could not the captured electron be acting as a wave as well? Because like I said, atoms and molecules, they also wave.
Yeah, well, I think the whole idea of electron microscopy is that the wavelength of the electrons that they're using is very, very tiny, as opposed to the wavelength of light. I think that's
Yeah.
how that works.
For
Because
bound electrons, that's like the Schrodinger model. And it's worth noting and even emphasizing that Schrodinger never liked what Born said about his model, that
Here we go, philosophy again.
yeah, that it's all just probabilities. And Schrodinger, he had different ideas there. People still like his equations, and it is off of waves.
But you want realism. You want some kind. So what we're trying to do is we're talking about things with realist
Yeah,
concepts.
I think Schrodinger actually was a realist, not Born, but Schrodinger.
Okay, I see. So when we're
He would have
talking
been
about,
opposed, maybe. Well, they're complementary, the Heisenberg approach and the Schrodinger approach.
I don't know that Heisenberg was a realist. He has the matrices, and it's hard to see how to be a realist with the matrices. But Schrodinger, you actually read him, I think he was a realist about his waves.
Obviously, I suppose to accentuate that, this cat business, which is frequently cited, I think he introduced that to show the nonsensical nature of this, non-realistic
You're
approach.
absolutely right there. I've read the paper, and you're absolutely right. It was like to show that quantum mechanics, the Copenhagen interpretation, has unacceptable consequences. The cat that's in a superposition of being dead and alive, which, at least for Schrodinger, that was nonsense.
Oh,
I
that's
can,
just crazy talk.
yeah.
so there's still the predicament is this idea of that if you want a we're talking in realistic language when we talk about electrons. Electron does this, it has these properties. That's a realist type of concept, right?
Hmm.
And then when Rick is talking about photographs or these electron micrographs or whatever they call them of atoms, you can actually see the atoms there. And
In some
so
sense of C. Yeah.
yeah, right, exactly. So you're thinking, well, that atoms, these pictures are real of atoms. This is what they really look like. Okay, so we're talking realism there, but then that the other way of talking about it is through mathematics and and these wave functions and probability distributions and
In what sense of probability you have going on there, but
right. Um, that's not realism. That would be
if it's the propensity sense, that's not realism. The ignorant sense, that is realism.
oh, I see what you're saying. Okay. So we have to sort of differentiate what we're talking about
Mhm.
Well,
I
math
wonder,
math can
I
re math
wonder,
math can perfectly represent reality, and math can perfectly represent fakeness. And it's been proven that math has propped up models, but they've been proven to be wrong. So math is just a tool. You,
well,
I don't put any credence in math other than validation of an experiment. That's
right,
it.
but you have to understand that the physics operates under a philosophy that the world is mathematical. Okay, that's a philosophy that exists in physics. And so the reason they use math is they believe that they can discover the mathematicians believe they can discover the secrets of the universe purely from math. You
Mhm.
understand what I'm saying?
Oh,
Yeah,
exactly.
you can almost have numerology there, saying numbers are basic. The Pythagoreans, the ancient Pythagoreans, they actually said something like that, or the music of the sphere, which actually Kepler believed in.
Right.
Yeah, or I've seen people like go at I'm trying to think of his name at Cornell. He says like you have information without anything that the information is embedded in. And I that type of talk it kind of bothers me because you have like something abstract as being what's basic, and I don't see how something abstract can be basic. Plato talked that way at times with his forms. You have abstract forms of like goodness and stuff, and then things partake of it. So there have been people who talk this way, but I don't buy into it. There I agree with Plato's student Aristotle, who was a nominalist, so abstract entities don't have an independent existence. But you do get physicists now. They seem to be Platonists.
Yeah, that's very. So what is nominalism? Could you?
Abstract entities don't exist. Something concrete can have a property, but the property doesn't exist apart from the object.
Okay.
So numbers, and some mathematicians are Platonists, and they say numbers literally exist. I don't buy it. You can
So
use
number.
numbers to describe like plurality and stuff, but
So numbers are a kind of an idealist. Um,
idealism has more than one meaning.
I
One
know.
meaning is everything that exists is mental. The second one is that abstract entities exist. And they use the same word for both, which causes confusion.
Right. But mathematics, in my view, is idealism.
In the sense of abstract entities, yeah.
Correct.
At least if you're a Platonist in mathematics, and evidently that's the most popular position.
Right. So what your model though is you're looking for something that's not mathematics. It's not. It's
Something that actually exists as an independent existence, yeah.
right. But
And it's
physics is
not it's not
okay.
part of the mind either. So I'm not an idealist in either sense.
Okay. Right. So back to the covalent bond, then would it be possible to think that there's a wave that surrounds both of the atoms, that this electron is not really an entity that's a point that needs to be shared, but it's spread out.
I think it's spread out, and I think it's spread out as a shell. My first
Okay,
thin
so
shells are electron orbitals,
okay, so you're thinking
but
about
they have integral spacing for the electron orbitals. It's only afterwards that you get the inverse square rate occurring for
okay.
the thin shells.
So
I was curious in your slide on the covalent bond, you included deuterium there,
Yeah,
which is what, an element.
that's
And
right.
so it's not really a covalent bond.
You're absolutely right, Jim. That one wasn't a covalent bond. It's the second one, the H2. Okay.
Okay, thank you. That clarifies it for me, because I was wondering why you put deuterium in a slide on
Yeah,
covalent bond.
but they both have two nucleons, but there's a separation between the two nucleons with H2, but not with deuterium.
well, then Jim kind of
Correct.
leads to the other idea that might be better if you put up your diagrams again. Um, so you're you have kind of do you have like a shell model for nuclei, or do you see the nuclei as being spherical?
Spherical adjacent to each other. I don't have they're not shells, at least with my model or my
Okay,
current
but what
model.
about the nucleons, the protons and the neutrons?
Now that's a good question. A lot of people say like uh, neutron, which of course is electrically neutral, is a combination of an electron and a proton, which would sort of imply an internal structure. I really don't have a model of the internal structure. People bring in quarks and things, and where you have like one-third charges and stuff, and I don't know how much of that I want to buy into. And some people may treat that as a calculating device, and some take it literally. But yeah, I really don't have more detailed models there.
That's where Ito would come in, Harry. His model shows you, in fact, uh, uh, shows you the structured model, or structuredatom.org shows you and allows you to build atoms with their model geometrically. And his part of his model of the atom includes the neutron as an electron proton pair.
That raises the issue as what does that really mean? I mean, electron, proton, that are they point particles that are just smashed together, or are they
They're combined in some way, in some process that makes them part of the atom. I can't explain it. If I could, Nobel, right? But
I think his idea is that has to do with from what I gathered from his discussion last week, that had to do with the mass differences, and
Mhm.
that was
Well,
his.
that was the difference, the mass differences between a free neutron
Right,
and a neutron in an
right,
atom.
right.
That was the differences that he was talking about.
So
Free neutrons are very weird. I've known of experiments and they go through walls and things, and you still get interference patterns. And the more I looked at it, just the odder it got. So I
Well,
definitely don't have a
Robert,
model of the
have
free.
you have you looked into Leonard at all?
Who's that? Leonard? No,
Leonard, LENR,
no.
low energy nuclear reactions.
Oh, right.
They have these objects called EVOs. They go through anything. I mean, like they tunnel into objects with such high energies that they pass right through them. It's amazing. And these, or sorry, the energetic vacuum objects. And wow, it's just amazing what Leonard is starting to show us. Cold fusion, in other words,
Uh,
Fleischmann ponds, right? It
yeah,
there's some
yeah.
transmutations going on there, and we can't explain it.
Well,
But
it makes more sense if the world is really waves and particles are kind of an illusion.
I don't think you
oh,
even have to call them an illusion. It's just that they don't fit the traditional picture of a particle.
Well, yeah,
But
that's
you can
a
have
different
discrete
way.
properties with something spread out.
Yeah, well, I don't know. I just, our high the language that we're using is kind of a roadblock, I think.
I agree with
how
you
can a
there,
wave
Gary.
curl into itself to then create a point particle, and then those point particles combine to create masses of
Right.
elements? So I mean, there's some magic going on there that is not understood. And until we understand it, we're just going to be scratching our heads going, what the?
Yeah.
Well, that's what we have now. We have, yeah, this kind of confusing quantum mechanics, nonsensical, and then philosophy gets into it and sort of points out absurdities.
Not all philosophers even take them as absurd. I, yeah, I don't know. You do what you can, and this was about as good of a model as I was able to come up with, and I really would appreciate feedback, and the more detailed, the better. I gave my email address, so it's the saying it's about as good as I can get it, but maybe with working with someone else, it's possible to get it somewhat better.
So,
I don't
have
know.
you had conversations with Harvey about this?
Not this particular part. He keeps referring me to various people, and I don't know. And then whenever we contact those people, and I find this is typical, someone just isn't interested in communicating about something. They have their model, I have mine, and it's like never the two shall meet or something. I don't know.
Yeah,
That's a
that
big
seems.
problem with egos even in this particular group. The egos just can't allow for other people to look at other models.
Yeah.
I have no skin in the game. I don't have a model.
Okay.
I look at the electric universe and I see so much that makes sense from even like a layman perspective, but you have to make some jumps of help me out here. Faith. You have to have a little bit of faith that what they're saying is correct, and how, because I don't know, it's just egos get in the way of
Well,
people learning
that's,
about other person's models.
I was
Well,
interested.
For
Okay,
a
go ahead, Ian.
mainstream response, I'm just wondering, your paper there, which Harry gave us a link to, Bob, have you published that?
It's very hard to get something like this published. It's just the truth. I've tried a few times. I've had other stuff published. I just had a book I co-edited, published by Springer, for example. And I sent them to see if they were interested in this. I didn't even get a response back. So I'm satisfied at this point keeping it on my website, and it's free for anyone to download. And I give my email address there, and I get almost no responses. So I don't know better ways to publicize things, but doing a presentation with a group like this, you get at least some people hearing it.
You're like the guy yesterday who's standing alone on the dune in the desert.
Yeah.
Mhm.
I thought that was I really like that, because that's the dissident dilemma, I think.
well, I think you would get 100% response, and I'm thinking also of Vladimir's talk about how many hundreds or of people that he's contacted without getting a reply. I think the secret is, when you contact another investigator, don't even mention your own model at all, period.
You may be right.
But what you do is you ask them about some question about their work, their experiments, their model, and you're pretty much guaranteed to get a reply. That reply then can lead to other questions, or then a response of what you think about their answer and why you think it, and perhaps further questions. But if you contact other investigators, simply presenting your own model, theories, thoughts, basically that's spam. For example, for some reason, in my email, I might be getting up to 50 emails a day of various people. I won't mention names, but probably the rest of you are also receiving these emails, and they're all spam. Not a single one of those emails asks me about my work. They're all,
So you're referring to Franklin Hugh and
yeah,
some of
yeah,
those
there's a
guys.
whole group. I don't want to mention names, but yes, Franklin and this Okindo guy, or Monday Tumbe.
I think Cornelis, who is listening to us, is also involved in that.
Yeah.
Yeah, I mean, and this is, so why these people are sending out this spam, I wish they would just take my name off the list, because, I have to spend a few minutes every day deleting maybe 20 or 30 emails, which are all spam. Not a single one asks me anything about my own work. And
Okay,
so,
well, maybe you should do that.
do what?
Suggest just ask them to delete your name from the email list.
Well,
I know the issue. I get those emails. I just delete them. I have this tablet computer, and it has this function in it where you can just go through them and just push delete, 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 and you can do it in like 2 minutes.
right, and then they go into trash, and then you have to go there and delete everything in trash.
Well, usually
So,
does it. Yeah.
but so that the mystery of Vladimir was wondering why he's not getting responses to many, perhaps hundreds of emails he sent out. The reason why is you're spamming people. And what you need to do is, for each person you send an email, ask them a question about their work. In a few cases, in my work, I wanted some answers from certain investigators, and I wrote them. I didn't mention what I was doing, except that I was interested in the topic, and asked the person a question. And these were top physicists in publishing in Nature and other mainline journals. And I always got an answer, always, 100%. Okay. So that this idea of sending out spam is not the way to engage with other investigators. The way to
Well,
engage
I
is
can,
to ask questions of the person about their work, their publications.
I agree with
And
you
you'll get
that
a
that
response.
works. I agree with you. That's a better approach. But I'm not really sure that, well, okay. I'm not sure what happens if you try to get the other person interested in your ideas or not.
Mhm.
Well, that depends
I do
upon the
know, I
will.
do
You
know
know,
from many
you
years.
have to respect that people are free to spend their time and distribute their interests according to their own desires
Right.
and free will. If you're approaching and saying my motive or my goal is to basically promote myself, that then then you're pretty much doomed to fail. Okay. You know,
Well, you can say your goal is truth. You don't have to say it's yourself, but sometimes you need feedback on your model just to get closer to truth.
well, you know, like one can get feedback um, eventually, because if you engage another investigator probing their thoughts on their work, they might then become interested in what why you're asking certain questions and what your response to their answers are. In other words, you develop some sort of a relationship or a conversation with
Actually,
people.
you can even work on someone else's model and not believe in that model, but still like point out, some like consequences of it or problems with it and things like that. And you don't have to believe
Well,
any
not
of it.
not only that, you may be able to take a piece of someone else's model and fit it into yours.
Oh, sure.
I
Okay, we're
mean,
coming up towards the end here.
I'll give you an example. Oh, excuse me, there's not time.
Got about a minute. Go ahead.
A quick example was when on the uh, electron dipole moment. It was a number of investigators over the years, both in England and the U.S., are getting this value very close to zero. In other words, a zero electron dipole moment, and this was suggested to indicate that the electron shape must be a sphere. So I wrote the authors of the latest paper and asked them, or asked the principal author why he chose a sphere. For example, a spinning top would also have a zero EDM. And I got the answer back, which was sort of like, I'm sort of dumb. Uh, that's just what everyone would think it would be, a sphere.
The way people in academia respond to questions from people who are, anyway. Okay, we're back.
you're stupid. You don't know.
Strategic means for getting some feedback on one's own system. I mean, certainly one shouldn't go in and say, "Look, I'm the great person. I've developed this." One should indeed, as Jim says, maybe inquire about the other person's work and so on, and maybe that could lead eventually to a discourse in which your own ideas could be mooted.
Mhm.
Well,
Just
plus
watch the
you have to consider also James's problem with the myriad of emails that come in. These people also have a myriad of emails come in, and maybe they just don't have time to talk about other people, make friends with other people and things like that. So there's that aspect as well.
an example of what I'm saying actually occurred in yesterday's video of the CNPS meeting hosted by Ian, our great Ian Cohen, of Frederick, I guess it's Lassalle, or I can't pronounce his last name, is a French guy. And I asked him several questions about what he presented yesterday. And after he answered those questions, I indicated something in my work pertinent to his answers. Just a little phrase. And he immediately wanted to know where he could read about that. And I gave him a link as to where he could find my papers. So an actual working example of the approach I'm suggesting, which is not spamming other investigators, but asking them about their work, is a way to develop a conversation. And, if there's merit in what I am doing, he will recognize that or not, according to his own, independent investigation of truth, as it were.
And you didn't push it too severely, which I think was a correct thing to do. I think at one time you said, "Oh well, today is not about my work; it's about the subject of today, which is our speaker." So that was, I think, a strategic way of drawing the man out in the first place. It was the correct thing to do.
Yeah,
Well,
good on you,
thank you
James.
for saying that, Ian, because I sometimes it doesn't happen too often. We have a really nice group here, I think. People don't really barge in but occasionally we will get an individual that'll take over a meeting and filibuster about their own work, but they're not the presenter. I mean, this again is spamming the video conference, whether it's the CNPS meeting or Harry's cosmology sessions.
Okay,
I'm
well,
sorry, James.
Go
ahead. Is that Rick?
Yeah, I was just apologizing to James.
All right. Well, Jim, do you have any?
You're sorry for what?
You felt a bit guilty, did you, Rick?
Well,
Okay.
I often spout off about the electric universe when,
Right.
maybe I shouldn't, but
Okay, Jim, do you have any questions or comments or feedback for Bob?
Let's see. Oh, let's see. The spotlight. Do I have any more questions? I'll think about that and chime in a moment. Well, one thing that sort of bothers me is this distinction, which I think Harry was making, of that a probability distribution is sort of not realism. Okay. Well, in statistics, you can take real things like people, male and female, and write and create it, or IQ test scores or personality test scores or whatever, and those are real things. Yeah. And make a probability distribution of the incidence. It's just called a distribution, a histogram is what it's called.
That's Jim. That's using the ignorant sense of probability. It's the propensity sense, which a lot of physicists use, where it's very unclear about how something is supposed to exist. But in statistics, it's almost always they're using the ignorance of interpretation. You have large numbers. You talk about the probability of someone not, of course, existence, like having a certain like IQ or whatever, and you have that distribution, and the people are real, and IQ in some sense is real, but that's just saying we don't know for that particular person, so we just talk about their chances of being it.
So the whole idea that simply by talking about a distribution or a probability distribution, the underlying events can't be real, is could even be applied as a critique of what you presented today, Robert, that because you talked about how things are, I guess electrons are distributed in various shells. And
no, I wouldn't say distributed. I would say spread out over the shell. It's not that they have a precise position within the shell. I have them spread out over the shell.
Okay, yeah, thank you.
Yeah, I think you're raising the issue that, where people are getting hung up. I have a problem with the fact that, to me, it looks like mathematical idealism combined with probability, in that you have a wave function which is solved through the normal classical methods. You have a wave that's solved classically, and then that's combined with a probability distribution. The wave, this classically solved wave function isn't a wave, but it's a wave of probability. You see, what does that mean? That's
Yeah, it even gets worse because they have probability amplitudes, and you have to
right.
multiply one by its complex conjugate, and then you get your probability. And I don't know.
That's basically, it's mathematics. It's saying that the atom obeys mathematical rules. And then it's sort of made to be physical by saying that it's a probability distribution. So when you make a measurement, then you get that. That's how the mathematics is connected to the measurements.
Right. So they make measurements as basic, and the older Bohr, he buys into all of that. And something really isn't there until you make a measurement. Or I think John Wheeler once said like something like "to be is to be measured." Before
Right.
that, for a while they had verificationism and logical positivism, that it's meaningless even until something is measured or it can be measured, and that they never
It's
really were
just
able to get that to work out very well.
it's just putting math on the pedestal again. It's
Right.
putting math up there and saying, "Oh, math, show us what's reality." And no, we have to figure that out for ourselves
Yes, but
in
Rick,
experimentation.
my view is that if you're the wave function that they get, this wave description that they get, my view is that's really what an electron is inside an atom. It's a wave.
Well, that's what Schrodinger tried to say.
Correct. That's my view. Right.
Yeah, but it's not. But then Bourne put in the probability interpretation.
Right. And
It could be something entirely different. It could be the expansion of an electron to encompass the atom.
Maybe.
I think a proton is the same thing as an electron. It just has more photons in it.
Well, it also has opposite charge and different mass, so you got to have some way to explain that.
And possibly more photons in an object would possibly change its polarity.
Yeah. Then you have
This
protons.
thing is nearly 2,000 times the mass of the electron.
Yeah. Well, then you have photons as being your basic entity, and raise questions how they exist. I don't know.
Well, we know they're emitted from every sun that we see and every galactic center and every plasma cloud. We know they're,
And every lamp and every any number of things.
yeah, but I mean, a sun is in my view in arc mode, an electric discharge in arc mode.
Mm-hmm.
And if everything is electric, then all of those other sources are as well in arc mode,
Yeah, I
producing
partly agree with you there. Electric charge for me really is a primitive. So,
yeah, it's primary. It's primary in the universe. I think the potential between charges and the potential between like charges is how the universe runs.
hmm.
Fundamentally, anyway.
Okay. Well,
I'm sort of in the strange position, having presented here on a previous Sunday a whole session criticizing quantum mechanics and enumerating its many, many limitations. But now I'm going to defend this idea of the probability distributions, because the investigators in using quantum mechanical theory claim to have uh, uh, demonstrated up to many, maybe half a dozen or more significant figures, certain quantities which are measured and showing quite a bit of an amazing degree of accuracy. And so the idea of sort of putting probability distributions and what is real or not real as opposite poles of some spectrum, I think is a questionable approach.
Well, I disagree.
Okay.
That's the situation as it stands. There's no common ground there between the two. I'm not really sure what, from my point of view, I don't really know what it means, probability distribution. I don't know what that means. It doesn't mean anything to me.
Well,
It just
in,
means the
in
electron could be
elementary
here or
statistics,
there
there's a
or
thing called a
there.
histogram. That's an elementary statistics.
I don't know.
A histogram.
Yeah, you could say that, but it doesn't convince me of anything. It's just words, doesn't convince me, doesn't have any impact on me to persuade me to imagine that that's real in other words, Bob's talking about realism, and I'm sort of taking a realistic approach. I believe in realism too. So what is it? I don't believe that electron is necessarily a particle.
Well, you got to
Let's say
rework the concept of a particle, I think, but
let's say a histogram of the age distribution in decades of the population in a particular country. That's
but an age
very
distribution
real
isn't a physical thing.
representation of a very real thing.
yeah.
But that's
No, you're
not
right, Jim. That for your example, that works, and that's the ignorance sense of probability. But it's not clear that's the sense used by people doing quantum mechanics.
Why is that, Robert? I mean,
Because they talk
I'm not
about.
being combative here.
Hold on.
No, it's okay.
You have to.
No,
Robert's trying to explain this difference in the senses of probability, and it's kind of a fine point. And I
Okay.
kind
So
of
let's give Robert a chance to explain, what he was going to say a moment ago.
Yeah, okay, yeah. They used, well, I know like my thesis advisor, Abner Shimoni, he, like you've heard of like John Bell and Bell's theorem and things like that. And they said that that was evidence against local realist theories. For me, the problem was local. I say that things are holistic, but they took that as evidence against physical realism. They said that just the basic principles of quantum mechanics are not compatible with local realism. You'd have to look at Bell's papers, The Speakable and Unspeakable in Quantum Mechanics is a collection of his papers. Yeah, so he took that as being a refutation of at least the local realist theories. And like with your examples, Jim, I think all of those are examples of local realism, like IQs of people and things. The people exist in a particular location and things like that. So they have local properties.
Okay.
If you look at this at the atomic level, I'm not even touching it. So I'm throwing a wrench into realism right there. I'm not even touching this. If you look at it at the atomic level.
Okay. But you have
I'm
bonds and things connecting the atoms and things. So
no, actually, my finger against the plastic, there is space between them. There's no bonds other than the electric charge of my finger against the electric charge of the plastic.
yeah, well, at least I'm a realist about fields, so I would say that the fields are there, and
Yeah.
How do you know, Rick, that the electrons in your finger aren't exchanging with electrons in the
They
poker
are.
chip you
The
got?
charge, bottle cap, Coke bottle.
And, how do you know that those are as physically separated as you seem to be saying? could be the electrons in each of the two objects. Your finger and the bottle cap are running back and forth between the two when you're holding that bottle cap.
I do believe they've done the experiments with electron microscopes, bringing two materials together and showing that they don't actually touch each other.
Well, that assumes they also you have a sharp boundary, which you may not have.
Yeah,
Well, depending on the material that you're using,
Yeah, and
it
you
will
know,
or
if it's
will not have
adhesive
that
or
sharp
something,
boundary.
then you might
Yeah.
actually have a chemical bond even there. But
Those electron microscope images only show the atoms. They don't show the detail that I was referring to.
Well, they show the electron shells. The outer shell of the atom. They show those. They don't
But they
show the
don't, for
atom
example,
itself.
exclude the possibility of electrons going from one object to the other, whereas you're claiming that they're actually separated in
By
some
charge.
absolute complete
By
manner.
by charge opposition, positive to negative kind of thing, where you bring two magnets close together. If they're the right polarity, they'll. If not, they'll push away from each other. That's what's happening at the atomic.
That's where we get
Whatever is
confused.
happening, I mean, what you're describing now is a difference in macroscopic perception from perhaps what is happening microscopically. So, in other words, we feel that we're in contact with something, but that doesn't necessarily mean that we're in absolute contact at the microscopic level.
That's the conundrum of, I was pointing out what's reality.
well, both your experience is real, and I think the object is also real. And actually, I'm a dualist there. So you have the space of like visual sensations, and you also have the world of physics, of physical objects, and I think both exist. I think they both are in space and time, different
Yeah, I
different
agree.
spaces. Yeah, okay. Well, actually, I'm going to give a talk on this at this. I gave one in San Francisco last April. I'm going to give another one to a philosophy conference in Baltimore in January. An awful lot of people in philosophy, they're direct realists. And the title of my talk is Direct Realism is Malarkey, which
What's
hopefully will
direct
get an
realism?
audience because philosophy is full of these direct realists that we're immediately aware of distal objects and we just aren't. It's a reconstruction from the brain that we're immediately aware of in some. You got to be real careful with your language there. So, but I think there's this phenomenal realm of like experiences. It's a conscious space, and there also is a distal space that's apart but in causal connection with it. Is that's the space of physical objects, and I think that realm also exists. So I'm a physical realist also.
But you draw
Robert,
in idealism in the other sense, about not having an objective reality apart from the perception.
Yeah,
So
that's
you said
Berkeley.
earlier, yeah,
Yeah,
Berkeley, yeah, yeah.
That's Berkeley. Yeah, I don't follow him on that. And he was.
could you remind us, Bob, of what how we define direct realism?
It
Like
has
your
more than one
adjective.
sense, but that we're immediately aware of distal objects. I open my eyes and I'm maybe even aware of your face, even though it's like on my screen and stuff. And it's
And
just
why is that malarkey?
because I'm not immediately aware of you. My awareness is a reconstruction that the brain has made. And sometimes it gets it wrong, like with optical illusions. It makes a guess, and sometimes it gets it wrong.
Okay.
And there's the mind-body problem, how the brain does it, and I don't think anyone has solved that.
The difference between sense data and the perception.
Yeah, I believe in sense data a lot. They get attacked a lot these days, but I believe, but it's misleading. It makes it sound like they're separated from each other, and instead there's a space like a phenomenal space, And if you can say it's comprised of sense data, but it sounds like there's just a loose collection of them, and that's not what's going on. But that's in the mind. That's in the conscious mind. But there is also a distal object. So I hold the causal theory of perception. We always see into the past because it takes like light time to go from the distal object to us. Maybe years when you look at a star, for example. They've gone out of existence in the meantime.
Okay, we got, looks like about 18 minutes. So do we have any more questions? So we have any feedback for Bob?
If anyone wants to send me an email, I had it on the screen about Robert period E period French at gmail.com. And I'd love to have like an email correspondence with anyone who has an interest in this or suggestions for changes.
All right. Well, I guess that's it. Any more questions? I think that's my second.
Well, I have a question for Robert. Your model of the atom, the stacking spheres, have you thought about a geometric approach, or it looks like you're kind of leaning towards the geometric
Yeah, it
approach?
is a geometric approach, yeah.
Well, then you might want to look at Ito's website and have
Oh, sure. How you spell his name?
Ito, EDO KAAL.
KAAL.
It's structuredatom.org, I think it is.
Structuredatom.org. Yeah, sure.
Yeah, have a look at his model because it's based on geometry.
Yeah,
And
well, we'd have that much in common.
yeah, and I mean, he's got some ideas about, again, the neutron being different inside the atom than a free
Yeah,
one.
I mean, pretty clearly there's a nucleus, and Rutherford, I think he was right on its rough size, 10 to the minus fifth the size of the rest of the atom. And there may very well be internal structure there. Uh, I haven't even tried to tackle it and how you go about it. It gets more and more speculative. Like you're pretty certain that atoms exist. What's going on inside, you're much less certain, and so you can try
Yeah.
models just to fit things. But
What's a proton? What's a neutron? What's an electron? I mean, we've got questions that have to be answered.
Well, what you have is those words that you just used, those are realist words. Okay, they imply objects that are discrete and have a separate identity from other objects.
Yeah,
right?
or mass. Yeah.
Okay, but when they go into the atom, into the nucleus, can you identify what these individual objects are, or are they just kind of
Well, right now it's all done through math. We
right,
can't see inside the atom.
right? So they're dependent upon whatever math model they're using
Yeah,
well, I mean, also,
to
they
interpret what's
particle
happening.
and geometric.
accelerators and things, but they smash them up and claim they can reach conclusions from that.
Well, the idea is that you take this physicalist interpretation, you take an object that you believe exists and you smash it against another object that you believe exists, and then you make inferences based on your math model.
Yeah,
Isn't that
something
how
like
they
that.
do it?
Something
And
like that, yeah.
and that assumes a certain realism. These objects that you're causing to interact are assumed to be real in Bob's sense of realism, I think.
Yeah.
But your inferences are really based on your mathematical analytical ideas, your abstractions that exist in the mathematical world. So you're taking objects in the real world and interpreting what happens to them in the mathematical world.
Hmm.
And you hope they agree. And when they
Yeah.
agree, you say your theory is proven correct.
Well, of course, it's not proven correct. You've just shown consistency.
Well, they
Yeah.
say proved.
They may say that. No, that's overstating it.
It takes an experiment to prove a theory, in my
Well, I
view.
guess a
Well, you
better
can
word
never
would be,
absolutely prove it. I think that's the point you're making. You
I
can
think a
disprove
better
it by
word
one
would be
experiment.
validate or
Yeah.
corroborate.
Valid, yeah, more so that's correct than proving it. But
Yeah.
with experimentation gives you physical proof that you're on the right track.
Yeah, you got to be careful saying that, but at least there's enough in common between what you're doing and the right track that it's. Uh,
So, Bob, do you have any ideas about free electrons? You make a distinction between what an electron is inside an atom and what a free electron is.
Yeah, I wish I did, Harry, and I don't. Because I know they have, like with diffraction experiments, they have wave properties. They seem to have also discrete properties like a particle. I'll admit they're a mystery to me, and things get worse with things with wave properties. Like you can do interference experiments not just with electrons and with neutrons, you can even do them with whole atoms, and the atom seems to have a composite structure to it, and how that is going to have a wave property. And I mean, maybe,
And molecules too,
yeah,
Robert.
even molecules, and whether you shift senses of probability here between an ignorance and a propensity sense. I don't have to me things get problematic all over the place, and I don't have a good handle on it.
Were you going to say something, Ian? I thought.
Well, unless you're reading my mind, I was talking, but there was something in my mind. Maybe if I just may say that quickly, Harry. Um, just about yesterday's speaker. I had a brief exchange with him after the lecture, and he may come back next year. But he said he's doing some work in cosmology, and I told him about the Sunday sessions. And I said they're convened by you, and he asked for your email. So I took the liberty of giving him your email. So he
Okay.
may contact you. I don't know.
All right.
Yeah.
What do you think about yesterday's talk? It's very interesting for me.
Go ahead.
Yeah. What did you think?
No, I'm asking you guys because I don't know what to tell you
Uh-huh.
about this talk. Mathematical, physical, I don't know. When he started from his empty space, immediately I lost him. Does it mean empty space?
Well, I think his idea is there is no empty space. That there's a medium, which he calls the surrounding, and
Round, what does it mean? I'm asking you because today we're talking about it's a real physics or it's mathematics only. And I didn't understand what does it mean, this variable gravitational constant, how it came, what is going on. Except some equations, I didn't see anything physical, I mean.
right. Well, that had to do with my question. I was kind of unsure what he meant by variable g. What is this g that he says is variable? I didn't really understand what that was.
I thought that was Newton's capital G constant.
Yeah, gravitational constant,
Yeah.
I thought.
Right, but
Yeah,
he
that's
was
what I thought.
talking about general relativity. What does it mean in general relativity?
He seemed to say that the G, which occurs in the tensor equation of general relativity, should also be variable. But I don't know if I misinterpreted him. I asked him for the order of magnitude. I thought he was going to say, oh, it might change by 0.1% or something. He said a factor of 40.
That's enormous.
Yes, exactly. So and I
Variable
asked him
in
maybe to
time, what does it
quantify
mean
this a bit,
variable?
give us a table of experiments using a constant G and using his values and where the differences are. And he seemed to shy a bit away from that. He said he might have done that on a previous lecture to some extent, but I think I've given him something to think about.
Well, the electric force is 39th to the power of gravity.
Yes.
So maybe that's where he's confusing his calculations or something. But that's all 40 and 39 is awful close together.
Okay,
No, he
Vladimir,
didn't say
what was
10 to the
your
power 40. He said a
Vladimir, what
factor
is
of 40.
Vladimir, what is your comment about this?
My comment is very simple. I did understand it. What does it mean variable? G, we know, everybody knows what does it mean G. Variable in time, in space, where variable? How it came from his equations, his long equation, and I didn't see any physical parameter in there.
Okay, yeah, that was my comment too. I had that. I wasn't clear. My here's my comment about this. I don't
Yes.
really see a difference between having a G constant in the equation being variable versus space and time being variable. So what is it? You know, I would have preferred a theory in which G is variable and space and time are constant, but I don't, if space and time can change, then G, to have G be variable doesn't, just is another point of confusion in my mind.
He didn't tell us what does it mean space and time. You know, I didn't understand any definitions even,
Right.
notion. You know, guys, we are talking about some variations, and I don't know what kind of variations of G.
When he was talking about space-time, he's talking about Einstein's space-time.
Correct.
So that's the
But
space-time he's talking
space-time
about.
of Einstein, it's geometry only. It's not physics, because the axis is ICT. It's complex number. What kind of space-time you have, man? It's
Well,
not physical.
Don't ask me. Ask him.
No, no,
He
you
seems to
this is
answer.
accept
a,
the general
Please answer
tenets
one more
of
time.
this
space-time,
is another
Minkowski.
example of what we were talking about for realism versus the idealism.
You
ICT that you
understood
just
me
referred.
correct. You understood me correct, because idealistic, okay, mathematics, all this, equations, it means for me nothing, because there is no physical issue. There is no physical definitions. There is no physics.
It goes back to mathemagic again.
Right.
Yes, not again. It's already 100 years already. Mathematics only instead of physics.
And
I'm so sorry.
I love you for talking about classical physics, Vlad. We should be going back to classical physics.
Yes, you're right. I came back myself 100 years, 120 years ago, because we cut our classical physics 1905. It's already 2025. It's time to come back, guys, to classical physics and forget
Well,
about all this
I think I would even
mathematical.
agree to the extent that classical physics is realist. They think what they're talking about actually exists.
Yep, exactly.
Are classical objects. We can talk about classical physics only. That's why all our imaginations about electron, photon, proton, whatever, it's our imagination. That's it. We cannot see them. We cannot ask even the question, what does it mean, free electron? I don't know. Somebody knows. Tell me how to define this free electron.
Well, it's quite radical because we're saying in a way that anything up to about 1900 followed a logical way of arguing, and mathematics was used, when it was necessary to quantify things, and anything after that was fantasy. As Helen Boutella said, anything after that will never be classical physics. You could go on for 4,000 years; it'll always be something completely out of our ken. So we're probably in agreement. I'm certainly an advocate of employing classical physics in those terms.
Of
I
course, what's
certainly
happened
subscribe
is
to that.
they expanded the concept of classical physics to include relativity, which I think was unfortunate.
Yes, we
Didn't
have
see even
met
relativity in his talk. What about relativity? Where is it in his talk? Guys, realism, as for me, it's a classical physics only. With classical objects, we can talk about something only from in a classical language. You know, that's why realism, all this quantum physics for me, it's not realism. It's our imaginations and way, mathematical way, how to explain what we can see in classical physics. The experiments, all the numbers we got for quantum physics, they are all of them classical. That's why where is its border, or there is no border between classical physics and quantum physics. And let me remind you one more time, Penrose, he killed already quantum physics. He told it it's contradictions. There are no physics. There are no, theory in quantum physics. And I believe Penrose.
Yeah.
Right.
And we're talking about what right now?
Yeah.
He
One
seems
point
to
is,
have engaged in rather a U-turn in recent times.
yeah. Actually, if you look at the old quantum theory, the old Niels Bohr, that was realist. But then it shifted, and one of the transitory figures was Schrodinger, but he was even realist. It's when they turned it
Okay,
all into
okay.
probabilities as basic.
Let me ask you the question about Sommerfeld. Do you know something about him? Because his theory was much better than Bohr theory. And nevertheless, he didn't get even Nobel Prize in physics. You know why? Because there was a contradiction immediately. When you are talking about the molecule of hydrogen, you have your problem with all these schemes, all these models about atom. Atom is good, but whenever you will try to combine two atoms, immediately you have your problems.
All right, we're
Immediately.
running out of
Yeah.
time here.
Yeah, okay.
Okay,
And for me,
Sommerfeld.
realism, it's a classical physics only, because all the rest, I'm not stopping them. Guys, it helps us with nuclear weapon, with all this stuff. I have no problem with it. But don't name it realism. It's not for me. Realism, it's only classical physics, classical experiments, classical numbers, and all this stuff. This is realism.
Okay, we got like a
Not
minute.
philosophical, but real physics.
Okay, all right. I'm not. I guess I'm gonna wrap it up here. Roger's going to talk next Sunday about his photography project that he's doing. Anyway, so that's what's scheduled for next week. I want to thank Robert for talking. We had a pretty interesting discussion. I'm not sure we gave Robert any real feedback that he's looking for. I learned some things. Thank you for that, Robert. I did learn some things. And so I want to thank Robert for doing his presentation. Okay, I don't know that we have any other here. Then I've got less than a minute before we get cut off. So thank everybody. And anybody, Roger, you have anything to say?
Yeah, see you next Sunday then.
Okay, what is it you're going to talk about now?
Astrophotography.
Astrophotography. Okay.
Okay.
All right.